Okay, let's unpack this. $1.4 billion vanished from Bybit. February 2025. I mean, it's potentially the biggest crypto heist ever.
It's a staggering number, definitely.
And the initial head scratcher for me, and I guess for everyone, was how? How could a huge exchange like Bybit, presumably buttoned up security-wise, lose that much?
Right. It immediately makes you question, well, what went wrong?
Yeah.
You expect multiple layers of defense at that scale. It wouldn't be just one simple mistake, you'd think.
Exactly. And as we started digging into the materials we have, the reports detailing the incident itself, and also this technical overview of Abatis Hard Disk Firewall, it became clear. It wasn't like a direct assault on Bybit's main fortress, so to speak. It was more subtle, a supply chain thing, targeting SafeWallet, which Bybit used.
Yeah, supply chain attacks are definitely a major vector these days. Sometimes it's, well, easier to go after a partner or supplier than the main target head on.
Yeah.
It's that trusted relationship that gets exploited.
Right. So, for this deep dive, we're going to walk through how this $1.4 billion theft actually happened, step by step.
Okay.
And then, this is the really interesting part, I think we'll look at how this different type of security, Abatis HDF, might have actually stopped it, like at several different points.
Throwing a wrench in the works,
Well,
potentially.
Yeah, exactly. So, understanding the attack and then seeing how a preventative tech could counter it. That's the plan.
Sounds good. It's crucial not just to analyze the how, but to think about proactive prevention for the future. How could this have been different?
Okay, so ground zero. Reports point towards the Lazarus Group, right? North Korean state-sponsored unit.
That's the attribution, yes. Known for sophisticated cyber operations, particularly financial ones.
And the way in, the first domino, was apparently a SafeWallet developer. How did they get to them?
It looks like pretty classic but effective social engineering. The developer was apparently lured into downloading what looked like a stock trading simulator.
Ah, the old fake software trick.
Yeah, but this one had malware hidden inside. It really highlights that human element, Technology is one thing, but people clicking links or running unknown software,
Yeah.
that's often the weak link.
And this malware wasn't just generic stuff, was it? It was custom.
Seems so.
Ah.
That's key because your standard antivirus or EDR, they look for known signatures, known bad behavior. Custom malware often slides right past because it's never been seen before.
Right, no signature to match.
Exactly. And then it apparently exploited a Python vulnerability. Python's everywhere, so a vulnerability there can be quite impactful. It likely gave the malware the foothold it needed to start doing more damage, maybe escalate privileges, without being detected.
And it stayed hidden for weeks. That's a long time.
It is. That dwell time is critical for attackers. They weren't just sitting idle. They were likely mapping the network, understanding workflows, looking for the crown jewels.
Which, in this case, turned out to be AWS keys.
That's what the report suggests, yes. They managed to synchronize their activities with the developer's work, stay under the radar, and eventually steal Amazon Web Services access keys belonging to SafeWallet.
Okay, AWS keys. For listeners, those are basically like digital master keys to SafeWallet's cloud infrastructure, right?
Pretty much, yeah. They allow programmatic access to cloud resources. So with those keys, the attackers could essentially act like legitimate users inside SafeWallet's AWS environment, bypassing perimeter defenses.
Okay, so they're inside SafeWallet's cloud. How did they get from there to Bybit's $1.4 billion in Ethereum? That's the next big jump.
Right. This is where the direct manipulation happens. Bybit, like most exchanges, uses cold wallets offline storage for the bulk of assets and warmer wallets for operational funds.
Standard practice for security.
Exactly. The attack targeted a routine transfer from a cold wallet to a warm wallet. Using their access within SafeWallet systems, the attackers intercepted or modified this process.
How did they just change the destination address?
It was more sophisticated than that, apparently. They injected a tampered JavaScript file into the SafeWallet web interface that Bybit employees were using.
Ah, okay. So manipulating what the user sees and does.
Precisely. When the Bybit employees went to approve the transfer, this malicious JavaScript running in the browser changed things behind the scenes. It led to something called blind signing.
Blind signing. That sounds bad, especially with crypto. What does that mean?
It means the interface, the screen the employees saw, showed the correct details, the right warm wallet address, the expected amount. But the underlying code, the actual transaction logic they were digitally signing, was different.
So they thought they were approving A, but they were actually signing off on B.
Essentially, yes. They were unknowingly signing a transaction that didn't just send the funds. It actually transferred control of the cold wallet smart contract to the attackers.
Wow. So not just stealing the money in that transfer, but stealing the keys to the entire cold wallet.
That seems to be the mechanism. They changed the ownership rules of the wallet itself on the blockchain. Once they controlled the contract, they could drain the funds. The JavaScript was reportedly very targeted, only activating for these specific Bybit transactions, making it harder to spot.
That's incredibly devious, exploiting the tech and the human trust in interface.
It's a potent combination.
Now, you'd assume Bybit and SafeWallet had security, right? Firewalls, antivirus, the usual suspects. Why didn't that stuff work?
They did have those tools, yeah. Firewalls, AV, EVR, threat intelligence feeds, a standard stack. But as we mentioned, the custom malware evaded the signature-based detection of AV and EDR initially.
Flew under the radar.
Right. And firewalls are great for blocking unauthorized access, but the attackers eventually used stolen AWS keys, which looked like authorized access from SafeWallet's side.
Okay, so the credentials bypassed the firewall logic. What about threat intelligence? Shouldn't that have flagged something fishy?
Threat intel often works by recognizing known patterns or indicators from past attacks. It's inherently a bit reactive. By the time this novel attack's indicators might have been identified and circulated, the Lazarus group was likely already in, had the keys, and was executing the plan. The damage was done before the alarm bells really rang loud enough.
So the traditional detect and respond model just wasn't enough here. Which brings us to Abatis Hard Disk Firewall. You mentioned it's different. How so?
Fundamentally different approach. Abatis isn't primarily about detecting bad stuff based on what it looks like or how it behaves. It's about preventing unauthorized actions in the first place. It's deterministic.
Deterministic.
Meaning it works based on fixed rules about what is allowed, rather than trying to guess what isn't. Its core idea is to stop unauthorized code from running or making lasting changes, period. It denies the ability to execute or modify, rather than trying to identify intent.
Okay, how does it actually do that? What are the mechanics?
Couple of key things. First, it effectively freezes the operating system and approved applications in a known good state. Think of it like making critical program files read-only. Malware can't write itself to the disk as a new executable, and it can't modify existing trusted programs.
So that initial malware download, the fake stock trader?
Exactly. When the developer tried to run it, Abatis would likely block it for two reasons. One, it would probably try to write new executable files, PE files, to disk, which Abatis prevents in unauthorized locations. Two, it might try to run directly from the downloads folder, which isn't protected permanent storage for applications. Abatis stops execution from places like that.
So, boom, attack stopped at step one.
Potentially, yes. That first point of entry could have been completely blocked. The social engineering would have failed to deliver its payload effectively.
Okay, but let's say, hypothetically, something got through that initial step. What about the Python exploit they used?
Even if the initial exploit happens, the attacker needs to run more code afterwards. They need to run tools to steal credentials, move around, communicate back. Abatis's rule against executing programs not in protected permanent storage is key here.
Right.
And it also blocks techniques called living off the land, where attackers use legitimate system tools for malicious purposes. If those tools are used in unauthorized ways or try to execute scripts from unprotected locations, Abatis could block those actions too. It contains the breach.
Okay, containment. Now, the big one, stealing the AWS keys and messing with the transactions.
Yeah.
How does Abatis's freezing idea help there?
That OS and application freezing is critical.
Yeah.
Even if attackers got some level of access, maybe through stolen credentials, they couldn't persistently modify core system files or the SafeWallet application files on disk to embed their malicious logic or permanently store stolen keys. Abatis would block those unauthorized writes to protect its storage.
It makes the system tamper-proof, essentially.
That's the goal. It hardens the system against unauthorized changes, making it much harder for attackers to establish persistence or alter critical software components.
What about that UI manipulation, the JavaScript injection for the blind signing? That seems like it happens in the browser, maybe harder to stop?
Well, Abatis doesn't read the screen content, no. But that malicious JavaScript, it still needs to execute on the employee's computer inside their browser process.
Ah, okay.
If Abatis is locking down the execution environment, preventing unauthorized scripts or code from running even within a browser context if configured correctly, then that JavaScript wouldn't be allowed to execute. If the script can't run, it can't manipulate the UI, it can't facilitate the blind signing.
So you block the execution of the malicious script, and that indirectly prevents the UI trickery and the blind signing.
Exactly. You prevent the root cause the unauthorized code execution on the endpoint.
Now, you mentioned materials on Abatis, mentioned logging, HDF logging. How would that have played into this? Forensics, maybe? Early warning?
Both, potentially. The HDF logging creates a detailed, secure audit trail of everything Abatis blocks. So in this scenario, it would have logged the attempt to run the fake stock simulator. It would log any attempts by malware to write executables or run scripts.
Right.
It would log attempts to modify protected system files. This log provides immediate evidence of an attack attempt. Security teams could see, hey, something tried to run this unauthorized program on the developer's machine, or something tried to modify this critical file. It's a huge early warning sign.
Way earlier than waiting for threat intel or noticing money missing.
Potentially, yes. And even after the fact, for forensics, that immutable log tells you exactly what the attackers tried to do, which executables they tried to run, which files they tried to change, even if they failed. It gives a clear picture of their methods at the endpoint level.
That sounds incredibly useful for understanding exactly how an attack unfolded or was attempted.
Absolutely. It provides ground truth about blocked malicious activity on the protected system.
So, pulling it all together, the real value here seems to be shifting from detect and respond to prevent. Abatis isn't trying to identify every possible threat, it's stopping unauthorized actions cold.
That's the core philosophy. It's proactive and deterministic. It doesn't need a signature for the Lazarus Group's latest tool. If that tool tries to write an executable where it shouldn't, or run from an unauthorized location, Abatis blocks it based on fundamental rules.
And it seems applicable beyond just servers, like on developer workstations, which we saw were the entry point here.
Definitely. Endpoints, servers, critical infrastructure, anywhere you need to ensure system integrity and prevent unauthorized code execution. Plus, it's designed to be tamper-resistant, making it hard for attackers to disable even if they gain some access.
Okay, so summing up this deep dive, a massive heist enabled by sophisticated social engineering, custom malware, exploiting a supply chain link, and clever manipulation leading to blind signing. Traditional security struggled.
A perfect storm of modern attack techniques, really.
But a technology like Abatis HDF, with its focus on preventing unauthorized execution and modification, seems like it could have potentially blocked this attack at multiple stages, from the initial malware run to containing lateral movement to preventing system modification and the execution of the UI manipulation script.
That's the analysis, yes. By changing the fundamental security posture to one of prevention based on allowed actions, you create a much harder target, irrespective of the novelty of the attack tools.
It really makes you think. In a world where these targeted, human-focused attacks are getting more common, maybe this kind of deterministic, proactive security isn't just an option, but maybe the necessary next step, focusing on stopping the ability to run bad code rather than just chasing the latest threat.
That's certainly the provocative question this scenario raises. Is prevention by design the future path, especially for critical systems and high-value targets? It's something worth considering.